In order to keep our word, we must give a quick overview of non-neural networks' machine learning algorithms, just so you have an idea of their existence. Throughout the whole course, we considered discriminative models. A discriminative model is one that uses an input and then provides a probability of whether an output is correct. Another instance of discriminative models are random forests. They are based on decision trees, and this is why they are called forests. The main idea is that decision trees are not so good at classifying, as they tend to overfit a lot. A random forest takes many decision trees and makes the point that many bad classifiers equal a good classifier. And that said, random forests are mainly used for classification. Okay, there are also generative models that don't give an output y given x. The target is actually the join probability distribution of x and y, which carries more information. It goes from inputs to outputs, and then from outputs to inputs. That's useful for problems such as translations. If you have an English to Mandarin translator, you'll probably want it to work from Mandarin to English as well. Or at least, you are going to check if it's working. Without going into detail, examples are hidden Markov models. Hidden Markov models assume that the problem at hand is a Markov process. Broadly speaking, this implies we can predict the future based on the present, just as well as if we had the whole history of the process. That, in a way, is opposite to what we've done so far. Then we have Bayesian networks. As everything that has the Bayes name in it, these models take into account prior probabilities. The difference between a neural network and a Bayesian network is that with Bayesian networks, probabilities of an event occurring are used as the model's inputs. In a neural network, each input alone doesn't mean much, but a model trained on many inputs gives amazing insights. Bayesian networks are quite useful when we have some uncertainty. For example, in medicine, a person may have a certain disease with some symptoms manifested, while another may have the same disease but with completely different symptoms manifested. This is a situation where we have conflicting information. A neural network would be confused, as there would be no trend to be found between the two patients, while a Bayesian network would assume that such a case is not unusual. That said, researchers create neural networks that are designed to reflect such problems with considerable success. We believe this was a good overview of what else we have out there. Neural networks are a great place to start exploring the machine learning universe. Moreover, it seems like they are advancing at a much faster pace than other types of machine learning. It's worth saying that they are so fascinatingly good at predicting that we humans are not quite sure why they beat every other type of analysis we've invented so far. Research is making way, but so far, no one truly knows why these structures solve problems with such high accuracy. However, not being able to understand them completely doesn't mean we can't assess them. And the verdict is 10 out of 10. This course was a great journey, and thus, we'd like to finish with some food for thought. Each problem, no matter if an image, a business problem, or a Shakespeare sonnet, tells a story. With the right tools, you can reveal it and take advantage of it. Now that you have completed this course, you have acquired some very valuable tools, and it's up to you to find and tell the right story.